Hi everyone. So in this video, we're going to continue off where we left off last time in exercise 2.5 of class 9 NCERT mathematics. And we're going to start with question number 8. So question number 8 is asking us to factorize each of the following. And the first part is 8a cube plus b cube plus 12a square b plus 6ab square. Now, looking at the powers of the variables alone, this seems to be an expansion of a cube. Let me rewrite the first term as the whole cube of 2a. So this is 2a whole cube plus b cube plus. Now I'm trying to write it in the form of the expansion of identity number 6 over here. So to get these two terms, I'll write this as 3 into 2a square into b, whereas the last one is plus 3 into 2a into b square. Now comparing this with the expansion of identity number 6, I can say that this comes out to be 2a plus b whole cube. Moving to the second part. Second part is 8a cube minus b cube minus 12a square b plus 6ab square. Again, this looks like the expansion for a cubic identity. We'll write this as 2a whole cube minus b cube minus 3 into 2a whole square into b plus 3 into 2a into b square. And this becomes 2a minus b whole cube, just like identity number 7. Moving to the third part of question 8, we have 27 minus 125a cube minus 135a plus 225a square. Again, let's represent this as 3 cube minus 5a whole cube minus 3 into 3 square times 5a to indicate the minus 3x square y part of identity number 7. I can just quickly check that this will be equal to minus 135. So 3 cube is 27. 27 times 5 is minus 135, the minus sign. So we're good. And this is plus 3 into 3 into 5a whole square. This gives us 3 minus 5a whole cube. Moving to the fourth part, we have 64a cube minus 27b cube minus 144 a square b plus 108 ab square. Again, let's try and fit it in terms of cubic expansions. Here we get 4a whole cube minus 3b whole cube. The negative term will be minus 3 into 4a square into 3b. We can validate this. 16 times 9 is 144. So we write this is plus 3 into 4a times 3b square. Again, 27 times 4 is 108. And so, using identity number 7 again, I get 4a minus 3b whole cube. The fifth part is 27p cube minus 1 by 216 minus 9 by 2 p square plus 1 by 4 p. Now converting this into the cubic expansion, this can be written as 3p whole cube. This becomes 1 by 6 whole cube minus 3 into x square y, which in this case is 3p square into 1 by 6. Sounds about right. Plus 3 into 3p into 1 by 6 square. And this looks like the identity number 7 over here, and hence we can get 3p minus 1 by 6 whole cube. Moving ahead to question number 9. Question number 9 says verify the following. And for the first part, we have x cube plus y cube is equal to x plus y multiplied by x square minus xy plus y square. What we're going to do over here, we're just going to focus on the RHS. So I'll say here, focusing on the right hand side of this equation, I'm going to open the brackets and let's see what we get. So we get x cube minus x square y plus xy square plus x square y minus xy square plus y cube. Now we can cancel out the terms which are the same but opposite in sign, and what we're left with is x cube plus y cube. Now we can see that the left hand side of the equation is now the same as the right hand side of the equation, hence verified. Moving on to the second part, similar to the first part, here we have x cube minus y cube on the left hand side. We need to prove that this is equal to x minus y multiplied by x square plus xy plus y square. Again, just like the first part, we're going to focus on the right hand side of this equation, and let's open the brackets. We get x cube plus x square into y plus x into y square minus x square into y minus xy square minus y cube. Again, we'll cut the terms which are same with the opposite sign, and what we're left with here is x cube minus y cube. And so we have shown that the left hand side of the equation is equal to the right hand side of the equation, and hence we have verified this problem. Question 10 of the exercise is asking us to factorize each of the following. The first part here is 27y cube plus 125z cube. Now, if we remember in the previous question, question number 5, we proved two identities, and we're just gonna use an application of them in this question. And just to remind, I'm gonna write the identities we proved in the ninth question. The first part of the ninth question proved that x cube plus y cube is equal to x plus y whole multiplied by x square minus xy plus y square. And the second part was x cube minus y cube is equal to x minus y into x square plus xy plus y square. So now, since we know and we proved these identities in the earlier question, I can simply use this factorization and apply it to our first part of question number 10. So I'm going to use this one. You could call it identity 9 in continuation and this identity 10. So the first part here is going to be like identity 9. Before that, I'll just represent it in perfect squares. This is 3y whole cube. This is 5z whole cube. And hence, in factorizing this, I get 3y plus 5z whole multiplied by 3y square, which is 9y square, minus x into y, which in this case becomes 15yz plus y square, which is 25z square. And that's the factorization for the first part. The second part is 64m cube minus 343n cube. write this as 4m whole cube minus 7n whole cube. Drawing similarities with identity number 10 over here, I'll get x minus y, which is 4m minus 7n multiplied by x square, which is 16m square, plus x into y, which is 28mn plus y square, which is 49n square. And that gives me the factorization of the second part. Moving on to question number 11. Question number 11 is asking us to factorize 27x cube plus y cube plus z cube minus 9 xyz. Now immediately I can think that this has three variables and it has a cubic power or degree 3, and hence I can use identity number 8 to solve this. So putting it in a form where I can use this identity, this becomes 3x whole cube plus y cube plus z cube minus 3 times 3x into y into z. And now using this identity to factorize, I get 3x plus y plus z whole multiplied by 9x square plus y square plus z square minus 3xy minus yz minus 3xz. And hence we have factorized question number 11. Moving to question number 12. Question number 12 is asking us to verify one more algebraic equation. And that is, on the left hand side we have x cube plus y cube plus z cube minus 3xyz, and on the right side we have 1 by 2 into x plus y plus z whole into, I'm just going to write this a little lower for some more space, whole multiplied by x minus y whole square plus y minus z whole square plus z minus x whole square So now again, what I'm going to do is simply focus on the right hand side over here. Focusing on RHS of this equation. And somehow I want to simplify this in order to see that if it's equal to the left hand side. So here, let's start with rewriting this as 1 by 2 into x plus y plus z, and out here I'm going to open these brackets by using identity number 2 three times, one for each of the terms here. So pay attention and you're going to see how this expands. So for the first one, I get x square plus y square minus 2xy. Expanding the second term, I get y square plus z square minus 2yz. Expanding the third term, I get plus z square plus x square minus 2zx. Simplifying this further, joining the like terms, I get 2x square, taking care of these, plus 2y square plus 2z square. And then I have minus 2xy minus 2yz and minus 2zx. These three terms as is. Considered all the terms. Now all of these terms have 2 as common, which I can take out of the bracket. And that way I'm left with x square plus y square plus z square minus xy minus yz minus zx. This 2 outside gets cancelled with the 1 by 2. And what I'm left with on the right hand side is essentially multiple of x plus y plus z whole multiplied by this polynomial out here, which is x square plus y square plus z square minus xy minus yz minus zx. Now this is exactly equal to the right hand side of identity number 8 that we have. And therefore, when we represent this identity in the form of its left hand side, I get x cube plus y cube plus z cube minus 3x into y into z. And now we can see that our left hand side of our original equation has reduced and become equal to the right hand side, and hence we have verified this identity. Now we move on to question number 13. Question number 13 is saying that if x plus y plus z is equal to 0, and this is given to us, we need to prove that x cube plus y cube plus z cube is equal to 3 times x into y into z, right? And for this, I'm just going to write identity number 8 out here. Identity number 8 is x cube plus y cube plus z cube minus 3 into xyz, and this is equal to x plus y plus z whole into x square plus y square plus z square minus xy minus yz minus zx. Now, in this identity, which we know is true, let me replace this guy, I'll call it equation 1, into our identity, which is equation 2. So, replacing or substituting 1 in 2, the x plus y plus z component in this bracket on the right hand side becomes 0. And we know 0 multiplied by anything is 0. And hence, our identity becomes x cube plus y cube plus z cube minus 3xyz is equal to 0. And now shifting the last term on the right hand side, I get x cube plus y cube plus z cube is equal to 3 times xyz. Hence proved. Now, before I move to question number 14, just reflecting on question number 13 again, I'm just gonna write what we proved over here, and I'm doing that so that we can use its application in question number 14. So we were able to prove that if x plus y plus z is indeed equal to 0, then x cube plus y cube plus z cube must be equal to 3 times x into y into z, right? And with that in mind, I'll move to question number 14. The first part says minus 12 whole cube plus 7 cube plus 5 cube. And I need to actually find this out without calculating the cubes, right? And over here, I'm going to draw parallels with what I just mentioned here. In each of these, where x is equal to minus 12, y is equal to 7, z is equal to 5, I can clearly see that x plus y plus z, which is minus 12 plus 7 plus 5, becomes 0. And if that happens, then the sum of the cubes of these, which is what we need to find out in the question, becomes equals to 3 times xyz, or 3 into minus 12 into 7 into 5. And we can calculate this by simple multiplication, and we'd have our answer without calculating the cube. So when we multiply this, we get minus 1260. The second part of question number 14 is similar. We have 28 cube plus minus 15 whole cube plus minus 13 whole cube. And here again, I'll draw parallels with what we have over here. In this case, my x is 28, y is minus 15, and z is minus 13, which means x plus y plus z is 28 minus 15 minus 13, which is again 0. And we know that if this is equal to 0, the sum of the cubes of the number is equal to 3 into x into y into z. So which means this, the sum of the cubes, is now 3 times 28 into minus 15 into minus 13. The minus signs get cancelled out and we can simply multiply these numbers. In this case, it is 16,380. Moving to question number 15, it's asking us to give possible expressions for length and breadth of each of the following rectangles in which their areas are given below. And the first part, we're given the area of the rectangle is 25a square minus 35a plus 12. Now, I'm gonna assume, or rather let the length of the rectangle be L, and I'm going to let the breadth of the rectangle be B. So now we know the area of a rectangle is length into breadth, which is equal to 25a square minus 35a plus 12. And essentially what we're going to do is we're going to try and factorize this polynomial on the right hand side in such a way that the two factors that we get, we will equate them to length and the breadth. So let's try and factorize this. I'm going to write this as a perfect square. So this becomes 5a whole square minus, I want to introduce the term 2 into x into y. So let me write this as minus 2 into 5a, and let's see what I'm left with. I'll need to multiply this term by 7 by 2 in order to get this. And I have plus 12 over here. Now, notice that when I do this, I can't really factorize it. The third term over here plus 12 isn't really 7 by 2 whole square. So that way I will not be able to factorize this. So if I do need to factorize this, I need to have 7 by 2 whole square. So what I'm going to do is, I'm going to add 7 by 2 whole square over here and also subtract 7 by 2 whole square over here. Since I've added it to this equation, I can take the first term, second term, and the fourth term, and combining this, I will get 5a minus 7 by 2 whole square. I've factorized this part, but I'm also left over with plus 12 minus 7 by 2 whole square, which is 49 by 4, right? Now let me simplify this a little further. I get 5a minus 7 by 2 whole square. I'm going to take common base of 4. 12 4s are 48 minus 49 by 4. And this is equal to 5a minus 7 by 2 whole square plus 1 by 4. Or rather, I can write this as 1 by 2 whole square. Pardon me. The sign over here is minus. And now, if we look at this carefully, this can be written in the form of identity number 3 over here. So let me just create some more space here and I'll continue with this over here. This is of the form x square minus y square, and factorizing it we get x plus y into x minus y. So my x over here is 5a minus 7 by 2 plus y whole multiplied by 5a minus 7 by 2 minus y, which is minus 1 by 2. This gives me 5a minus 6 by 2, which is 5a minus 3. This becomes 5a minus 8 by 2, which is 5a minus 4. And now that I know that my length into breadth is equal to 5a minus 3 and 5a minus 4, I can simply say that my length is 5a minus 3 over here and my breadth is 5a minus 4. I could have also written the breadth as 5a minus 3 and length as 5a minus 4. The only caveat over here is usually the length is the longer side of the rectangle than the breadth, and obviously 5a minus 3 is a bigger value than 5a minus 4 out here, and hence I have taken this to be the length and this to be the breadth, and that's my solution. Now the second part of this question, I'm given that the area is this polynomial out here, and I need to factorize it in such a way so that I get two factors where one will be length, one will be breadth. And how do I factorize this? I can use the method of splitting the middle term. Now I need to split the middle term 13y in such a way that for the two splits I'm getting, the two numbers that I'm getting, they add up to plus 13 and they multiply to get minus 12 into 35, which is minus 420. And the two numbers in that case would be 15 and minus 28, if I'm not wrong. So we factorize this as 35y square plus 15y minus 28y minus 12. I split the middle term like this. From the first two terms, I take 5y as common. I'm left with 7y plus 3. From the third and fourth term, I take minus 4 common and I get 7y plus 3 again. From this entire equation, I can take 7y plus 3 as common and I'm left with 5y minus 4. And so what we have over here is two factors where one of them is the length and one of them is the breadth. There can obviously be other factors that multiply to get this equation. This is just one such answer. So as long as you have two factors, multiplying both of them is giving us this. We can say that these are the possible areas for the rectangle, or the possible lengths and breadths of the rectangle. Question 16 says, what are the possible expressions for the dimensions of the cuboid whose volumes are given below? And the first part is the volume is equal to 3x square minus 12x. Now we know that in case of a cuboid of lengths, let's say L into B into H gives us the volume. So essentially what we need to do is we need to take this volume equation and we need to factorize it to get three different factors, and that could be a possible solution. So over here, we can take the volume equation to be, we can take 3 into x common and we get x minus 4. And now just visually inspecting this, one possible solution is length is 3, breadth is x, and height is x minus 4. That's one possible solution to this question. For the second part, we're given the volume equation to be 12ky square plus 8ky minus 20k. Now we need to factorize this in such a way that we get three different factors. So let me write on the onset 4 common from this equation and I get 3ky square plus 2ky minus, sorry, not 20k, minus 5k. If I also take k common, I get 3y square plus 2y minus 5. Therefore, I can assume that the length over here is 4, the breadth is k, the height is 3y square plus 2y minus 5. And that's a possible answer to this question. This brings us to the end of exercise 2.5. In case you have any questions, any concerns, any alternate methods, do comment over here and I'll be sure to reply. You can even reach out to me on the email ID mentioned in the description. Thank you for watching and stay tuned for future videos.